Okay, so let me get this to be full screen. Okay, that's where we stopped last class, where we were considering, remember, here we're considering both first, current in semiconductors. We talked about drift, how charge carriers move in fields. And we talked about diffusion, how charge carriers move in concentration gradients. And then we put them together to calculate the total current. Remember, we have 4 terms. We have electrons, we have holes. For each of them, we have drift, we have diffusion. Okay, so that's an important concept. Now, one thing we did not consider in the models was recombination. So whenever electron-hole pairs are created, they do recombine, and we lose them as well. So we need to account for that. Okay, that's where we stopped last time. So we looked at this very specific example where we looked at a slab of semiconductor shown here, p-type in this case. So we have hole current entering Jp shown here. Area of cross section is A, and we're looking at a very thin slice of the semiconductor, okay, in between x and x plus delta x. And we have a current going out, which is Jp of x plus delta x. Now, what we are interested in is how does the carrier concentration vary in time and in space. That's the goal here. In time, we can look within that little slab. Let's see what happens to carriers. So if you look at the rate of increase in hole concentration in the shaded volume, which can be written like that. So it's time rate of change of the hole concentration within that little region, x to x plus delta x. That's the rate of hole buildup. Is given by the holes that are entering, net holes that are entering the region, which should be equal to the current entering minus current leaving. So that's the net current coming into the system, into the shaded area. Of course, current by delta x gives you the unit volume, right? This is current density divided by delta x gives you per unit volume, which is what we're calculating. We're talking about carrier concentrations per unit volume. So this is straightforward. 1 over q, because the q is the charge carried per hole, minus what you lose by recombination. And that's the term we saw a couple of weeks ago and also very briefly last class. Basically, we have recombination rate that is proportional to 1 over tau p, which is where tau p is the lifetime of the holes. This is the average time that the electron-hole pairs remain separate. Average time between recombination events. Okay? And we saw that before. It's a negative sign because it decreases the total concentration because you're losing the holes, right? Okay, so that's a fairly simple equation. Now, of course, we can apply differential calculus by making delta x very small, and this becomes a partial differential equation, okay, as shown here. Okay, and that's a so-called continuity equation for holes. This is an important concept because we can use this to explain the behavior of almost any devices. These are the basic ideas which we will use to derive the properties of the devices later on. Okay, and the ideas are very straightforward. And the continuity equation just says that the rate of change of holes in space and time is given by, ignore that part for the time being, is given by the rate of change of hole current with space, which is basically how many holes are coming in to an infinitesimal region, net holes coming in, so coming in minus going out, minus how much you lose by recombination, which is just that term. Okay. Now, of course, this small delta p is defined as follows. So the total concentration of holes, which is now a function of space and time, is given by the initial concentration, which can be a function of space, but not of time, plus delta p. Okay? This is the excess holes that are generated. Of course, for most cases, we will ignore this, as in this example, because it's a uniformly doped semiconductor. Okay? So the total concentration is just that. This is a constant, so the derivative just becomes of that, right? Okay, you can write the corresponding equation for electrons. It's the same thing. except that now you have a change in sign of the current, because electron current is opposite to the electron flow, because it goes to the negative, right? So the same way you can write the rate of change of concentration of electrons is equal to the rate of the change of electron flux or the current minus recombination rate. Okay, delta n by tau n. Tau n and tau p are the lifetimes of the holes and electrons and holes respectively. Okay, this equation, of course, is time dependent, right? So we know in steady state there should be no time dependence. This equation should be equal to 0. Okay, at equilibrium, nothing can change with time. The current cannot change, the concentrations cannot change, so you have a steady state. So you set that equal to 0 and you get what's called the famous, this is applicable, what's called the diffusion equation, which is the same thing that you see in classical mechanics and so on. So anyway, you might have seen this before. Then if we make the further assumption the current is dominated by diffusion, so there are low fields, just in this particular case, then you can write the diffusion current. So this current term here is mostly diffusion, because we're ignoring the field for now. Then the diffusion current is just given by that, Q, the diffusion coefficient, times the rate of change of the concentration of electrons. The gradient of the concentration of electrons. Remember, diffusion depends on gradient, how the concentration of electrons changes with space. Okay, you plug that in, you get what's called the diffusion equation for electrons and holes, which basically, if you recall, we're just setting that equation to 0. Okay, and replacing that current by the diffusion current. That's all we did, and we get something like that, which basically says that the rate of change of concentration should be balanced by the diffusion current and the recombination. So the total rate doesn't change over time at all. Okay? This, by the way, is not necessarily steady state. This is also applicable for transient. We'll set that equal to 0 in a second, so I jumped the gun a little bit. So this, we haven't reached the steady state yet. All we have done is we've taken the previous equation, which is just the rate of change of the concentration of the carriers, replace the current by the diffusion current term, and then we have the recombination. Okay? Now, these equations are very important because it allows us to understand what happens in the transient behavior. So, for instance, if you have a photodetector, okay, if the photodetector gets photons, electron-hole pairs are generated. Because the photons convey energy to the electron-hole pairs, you get electron-hole pairs floating around. What happens to the device? How do we explain the current that you see? This is the equation we would use. Because what happens is, this is what you need to solve. If there's no voltage applied, that's basically diffusion current. So we have some boundary conditions. So initial conditions, we'll have some initial conditions. So your delta P, xt, and t equals 0 will be some, okay, this, remember this, we saw before, you have a slab of semiconductor, you shine light on it, you generate a pulse of electron-hole pairs very locally, right? That's this. This is the initial situation, right? And then it spreads, right? This is diffuses. That's exactly what happens in a photodetector or even a solar cell and so on. Okay? In those cases, we do have drift, but if you don't. So you can use these equations to essentially solve. Now, of course, to solve this is a partial differential equation, so it's not straightforward. It's a little bit complicated. But it's, we can make some assumptions to come up with some simpler solutions. But to solve this, just to remind you from your calculus, all you need to know is the boundary condition. So you need to know the initial condition, when t equals 0, and then you need to know some boundaries. So at some value x1, and delta p at some value x2, if needed. Sometimes you only need 2. Actually, there are only 2 variables. You only need 2. So this is just the boundary. Say, for instance, when x1 is very large, maybe we'll just say it goes to 0, which is typically the case. if it's far from where the carriers are generated. In any case, we'll look at an example, but just be aware of that. Okay? So essentially, these are useful to solve transient problems. The pulse of carriers are generated locally. How do they diffuse and recombine? So you can explain their behavior. Okay, so now going to steady state. Of course, in steady state, there is no time dependence, as I said before. You just set this to 0. Then you get the steady state diffusion equations. Essentially, you get this term. Okay, so you can look here, just setting that part to 0. So you get the second derivative of the carrier concentration with respect to space is related to the carrier concentration itself. Okay, this is the diffusion equation in steady state. And we can also define in this case L squared, where L is square root of the diffusion coefficient times the lifetime of the carriers, which is defined as a diffusion length. Okay. Now, we saw this partly before, and we will look at this more carefully. But if you think about it, the lifetime of the electrons in this particular case determines how long do the electrons last before they actually recombine. Now, while the electrons are not recombined, they are moving around. They're not sitting still. Okay? So the diffusion length is a measure of how far do the electrons move before they recombine. Okay? Now, this is important if you think about it. Imagine a solar cell where a photon came in, you generate electron-hole pairs. There is some characteristic diffusion length over which the electron-hole pairs will diffuse before they recombine. Recall, in a solar cell, the goal is to collect those carriers before they recombine. If they recombine, you've lost the energy, right? So you want those carriers, which means that you need to be able to place an electrode to collect them within a diffusion length, or within a few diffusion lengths. Otherwise, the probability of them being collected goes down. So it's a very important parameter for lots of devices. And we will look at this carefully again. So just keep that in mind. Okay. It is essentially the square root of the diffusion coefficient times the lifetime. That's the equivalent equation for the holes. Same thing. Now let's consider an example to make some sense of this. Okay, the example is very straightforward. Imagine a semiconductor bar, okay, and we are injecting holes here so as to maintain a constant hole concentration at x equals 0. So that's x. It's a one-dimensional semiconductor bar. It's a steady state, let's assume, but we are just constantly injecting holes. So that's the equilibrium situation. Okay, so delta P, the whole x's whole concentration at x equals 0 is some constant, delta P. Yeah, we can do this. We'll talk about how to do this later on, but imagine that you're just injecting holes. Okay? Of course, the holes will diffuse along the bar. Now, why would the holes diffuse? Yeah?
Because they're trying to keep equilibrium between the electrons and the bar.
Yeah, that's one way to think of it. But imagine, so remember what's going on here. So you have a bar, okay, that's the boundary of the bar, and you're injecting holes, okay? So if I draw the concentration of holes, okay, what does that look like? Before injection, okay, it's fixed, right? It's a constant. Something, it's pi or whatever. If it's intrinsic, it's pi, if it's low, whatever, right? As soon as this happens, you get a huge jump here, right? Right at x equals 0. So you have a concentration gradient, very high concentration of holes right there. So they need to diffuse, right? Go from high concentration to low concentration, which is similar to what you said, but it's the concentration gradient that forces them to diffuse. There's no drift, no field is applied. Okay? Now, of course, as they diffuse, as we know, they will recombine, and at some point they will die off. Basically, they will go away, right? So one would expect, so if I were to draw what happens in steady state, this is delta P, excess concentration of holes. They said to start with, let's say we had some concentration. Actually, delta P is the excess carrier, so this is 0 before you inject it, right? It's not nothing excess. Okay, that's just 0. As soon as you inject it, you will get a very sharp spike here. And then, of course, as you propagate here, you will expect this to diffuse and recombine and go to zero. When it's really far, it will all recombine, right? It will go away. So you would expect some sort of behavior like this. Okay, I want you to qualitatively kind of appreciate that before we go into the math. Okay, so that's what's shown here. So the concentration of holes in steady state looks like this. Of course, this is steady state because we are maintaining this concentration here by injecting holes. Okay, otherwise it cannot be steady state. Okay, so you expect some sort of behavior like that. This is the total P. When you look at delta P, it'll go to zero. But anyway, we'll come to that in a second. Oops. So let's concentrate here for the time being. Okay, so we need to solve this equation. This is the diffusion equation we just looked at. Change in concentration of the excess carriers as a function of time is given by the diffusion coefficient times the second derivative with respect to space minus the recombination rate. Okay. Of course, as I said before, this is a partial differential equation, so you have to kind of solve it. But there are different ways to do it. But here we'll just tell you the solution. The solution will be of this form. We know that in x you will have an exponential dependence, and that basically comes from this term here, if you think about it. Okay. So you have actually seen this before. So let me rewrite the diffusion equation again. So at steady state, this is very similar to the wave equation that we saw before. And we know a solution to this has to be an exponential, right? Because you take twice the derivative of the exponential, you get itself the exponential back, right? So we know that this is the solution. First of all, you see in the solution we assumed you have a plus e raised to x over LP term as well, but obviously that is meaningless because if x goes to very large, this will blow up, right? So that term that's not a correct solution. That won't make any physical sense because the concentrations cannot increase; they have to decrease. Okay, so we know that's not the case. So it has to look something like this because if you take the derivative, do you see that, first of all? You do very quickly. Okay. Let's very quickly work this through. What is that? I'll make that just a constant. You take another derivative. Okay? So, do you see that? LP squared is dP times tau n. Right? So you can see that's the solution, right? Now, of course, I wrote that delta P because that's a boundary condition. That's when x equals 0. Okay? So that's just this term here, this excess whole carrier. That's what you're injecting. So the excess whole concentration dies exponentially due to recombination, and we get an expression like that. So now we can write the total whole concentration as shown here, which is the initial whole concentration plus the excess, which is delta P raised to minus x over LP, this term right here. And now we can also write the currents. Okay, remember this is diffusing, so it has a diffusion current. And the direction of current is in the direction of diffusion of the holes. Okay, and of course we can calculate it. That's just we know the diffusion current is just the diffusion coefficient times the gradient. Right? We saw that before. And minus q, just because, recall, they go from high concentration to low concentration. So dp over dx is negative, right? Because it's decreasing. So you have to have the negative sign because it's in the direction of the decreasing concentration. Okay, we talked about this last class, so make sure you're pretty clear about that. And you can plug everything in, you get an equation that looks like that. So now you see that the current is also exponentially decreasing with position. Now you see why the diffusion length is important. This exponential dependence, of course, depends on the diffusion length, right? Longer the diffusion length, the slower this decreases. Okay, shorter the diffusion length, the faster this decreases. So again, if you had to collect this current, you need to make sure you can collect the carriers very close to your injection, depending on the diffusion length. Or you need to engineer your device to have long diffusion lengths, which turns out to be hard. Okay? So these are very important physical properties that people need to address while designing devices. Okay? Also true for all kinds of, some kinds of transistors as well, as we will see later on. Okay. So, again, to drive home this point about the diffusion length, which we'll come back to, we can do some simple calculations to understand what this physically means. Okay. So let's start with some very basic ideas. First, the probability that a hole injected at x equals 0 on the left-hand side of the bar survives until some distance x is given essentially by what the concentration of the holes at that location x divided by the original concentration of holes. So very simple, right? How many holes have survived? Okay, so let's go back to our picture. So imagine a semiconductor bar. X equals 0, some location x. We are injecting holes, okay, at the rate of delta p. The concentration here is that. The probability that a hole which is injected here reaches this distance is just that, right? The probability would be just delta p divided by the capital delta. Okay. How many holes reached there divided by how many started at the beginning. Very straightforward. So the probability that a hole at x will recombine within the next delta x. So within this region, the probability that the hole will recombine is given by how many actually recombined, right? So it's delta p of x minus delta p of x plus delta x. This difference is how many have recombined, because recombination is the only event which loses holes. Nothing else happens, right? It's just diffusing and recombining. That's it. Nothing else. Okay? Divided by delta px. So you normalize it. And if dx is small enough, you can write it this way using differential calculus. And from the equation from before, you get that. Okay? Dx over Lp. So this is the probability that a hole at some location x recombines in an infinitesimal distance dx. Okay, it's just dx over Lp. Now you can see why Lp is important. The diffusion length, in other words, is inversely proportional to the probability of recombination. Which makes sense because remember Lp is square root of dn tau n, right? dp tau p. And 1 hour tau p is the rate of recombination. Okay, from previously. Now we can combine these two terms and get the probability that a hole injected at x equals 0 recombines between x and x plus dx. Just multiply the two probabilities together. Probability that the hole reaches x and the probability that it recombines in the next infinitesimal distance dx. Okay, you get a term like that, e raised to minus x over Lp times 1 over Lp dx. You get that. Now we can calculate the average distance that the hole has traveled before recombining. I told you before that is the meaning of the diffusion length. Now we're proving it, basically. Okay? So this is the distance. This is the probability that the hole will recombine at x. Okay? If a hole injected at x equals 0 will recombine at some x. If you integrate this over all the possible values of x, you will get the average distance traveled by the hole before recombining. by all the holes. So you're basically statistically integrating over all the holes, as shown here. Okay, so we integrate this distance from 0 to infinity of that term times x, because x is the distance, times the probability that the recombination happens within that distance. That gives you LP. So if you do that integral. So in other words, the diffusion length is the average distance that the hole has traveled before recombining, okay, which is the same thing I mentioned before. Of course, this diffusion of holes results in hole current in the direction of decreasing concentration, which we know, we just calculated it. You can write that again as Jp of x is minus q dp, the gradient, concentration gradient of the holes. Okay? And you can express this in terms of excess carriers. Now, we know that and that's because we know that p of x is p naught plus delta p, right? And p naught is just a constant. So it drops out of the integral, a derivative. And you can plug that in, you get an expression like that. Okay, this is what you saw before. That's just the diffusion current also decreases exponentially, which, by the way, is why we need to have a good knowledge of the diffusion lengths in any material. Now, you might think this is a very simplistic example, but we will come back to this when we talk about p-n junctions, because this will be able to explain for forward bias p-n junctions in general. Okay, that's how a transistor works. Okay, we'll come back to that. So let's look at a very simple problem, and I want you all to kind of work it out yourself. So let's think about this for a second. In a very long p-type silicon bar, so it's infinitely long, with a cross-sectional area of ½ centimeter squared, the acceptor, so it's p-type, so acceptor concentration is 10 raised to 17 per centimeter cube. We inject holes such that the steady state excess hole concentration is 5 times 10 raised to 16 per centimeter cube. Okay, so p-type, you're creating excess holes at x equals 0. What is the steady state separation between the Fermi level and the conduction band at x equals 1,000 angstroms? Okay, so this is an interesting, and we'll look at the others later. So this is interesting, first of all, because. So let's just look at this. This is the situation, right? You have the bar, infinitely long. We're injecting currents to it. Let's look at the carrier concentration, excess carrier concentration. We know it kind of looks like that, goes to 0. Okay. Now, recall the carrier concentration. Now, if I draw the band diagram, valence band, conduction band, at location x equals 0, there are lots of carriers, excess holes, right? So my Fermi level has to be closer to the conduction band, right? As you go further away, the Fermi level has to change, right? Because your carriers are changing. So I would expect my Fermi level to go down as well, okay? Which means there is a built-in field in steady state that we talked about last time. Okay? Let's not worry about the field right now. Okay? So how would you calculate the Fermi level? Actually, I want you to discuss. This was you should be able to do this now because it was part of the homework last time, I think. So can you discuss with your neighbors for about 30 seconds or so? The first part of the problem. Okay, so how would we do it? Someone. So first, you don't need to actually give me the answers. Tell me how we would address this. So we need to know the Fermi level. So what do we need? just shut up. It's okay if you're wrong. We need, well, it's silicon. We don't need the band gap. Remember, we are trying to see where the Fermi level is with respect to the conduction band. So we don't necessarily need the band gap, but we know because it's silicon. All we need to know, let me draw the hypothetical diagram. This is the Fermi level, it's conduction band. All we need to know is this number. That's all we're asking for, right? First part of the question. What do we need? Yes, we need the total hole concentration at x equals 1000 angstroms. That's it. Once you know that, you know everything else. Why? Because remember, let's go back to the old equation. This is related to the density of states in the conduction band by something like this. Yeah? Actually, I forgot. But is it minus or plus? You guys should look it up or remember. Something like that, right? Remember, we talked about when these things get closer, this number goes up, all that good stuff. Okay? And this was just the density of states. Now, if we don't know this, we have other equations, of course, we can apply. Right? Or it's a silicon, we can always also look this up. So, I don't recall how they actually solved it. Let me take a look. Oh, they did it with the intrinsic carrier concentration. We can do it that way too. Okay? But anyway, it doesn't matter. So you have an equation that you can use to calculate the conduction density of states in the conduction band as well. Okay? Now, of course, we need to know this. And what's that? This is P naught. A 4 carrier injection plus delta P at x equals 1000. Right? P naught is just the acceptor concentration. That's what was there before you injected any holes. Delta P is just our equation. We just derived. Where is it? Yeah, this thing. So that's delta P injected at 0 times e raised to minus 1000 angstroms divided by LP. Okay? Just that equation we just calculate. Now we need to know is LP. LP is not given, so but you can calculate it based on the diffusion length. Okay? LP is so tau p is given here, 10 raised to minus 10 seconds. dp is a constant for silicon, so you can look it up in a table. Doesn't change. So now you know LP. If you know LP, you know this, how much excess carriers exist, 1000 angstroms away from the boundary. Then you add it to the total, you get the total concentration of holes at that location. Once you have that, you can plug it in here and solve for the Fermi level. Okay? This also you know, like the silicon level. Okay? In the text, they do it in a slightly different way, but it's the same logic. Okay, make sure you're very clear on this aspect of it, how to follow Fermi levels with carrier concentrations and so on. Wasn't this part of the problem set too? Wasn't this in the problem set too? No? No, not this, but calculation of Fermi levels, wasn't it? Okay, yeah. So you should be familiar with it now. Okay, the next question. What is the steady state separation between FP and EC at, oh, no, that's what we just did. What is the whole current there? That's easy, right? Because we just look, the whole current is just that. Current density is just that. Okay, so you just plug this in. You know Q, you know dP, you know LP, you know delta P, you know this term. We just calculated it. Okay, so that's the whole current density multiplied by the area, you get the whole current. So there's only diffusion current here. Okay, the next part is how much is the excess stored hole charge Okay, now for that, we need to actually calculate the total charge. So recall the whole charge delta P is the excess holes that are generated times the area, and these holes which are injected into the semiconductor bar will diffuse on an average for a distance of LP. Okay, so the amount of holes that are now extra holes that have recombined within the semiconductor bar, which because now they have recombined means you have excess positive charges, right? Because you're giving more charges there. That's the average number. Okay, times the area, because that's per unit area, times the the charge, electronic charge. That will give you the total charge. So this is a little bit counterintuitive. So think about this a second. So remember, you start with the neutral bar, semiconductor bar, right? You're injecting holes. You're injecting positive charges. Obviously, the bar, the charges are not going anywhere. It's getting more and more positive, right? That's obvious, right? That charges are not going anywhere. That's what this is calculating. So the average charges that are going into the semiconductor bar is given by the total charges that are injected in steady state per unit time, multiplied by how much they diffuse on an average, because they're recombined. Okay. Now remember, what does recombination mean? Recombination means the electrons that are floating around in the conduction band are captured and brought to a bond, to form a bond with silicon. And they go out of the conduction band. An electron is lost from the conduction band, okay, and an excess hole is there. Okay, remember the physical meaning of what a hole injection means. It's basically pulling electrons out, right? Which means you're removing negative charges, which means you're injecting positive charges. Okay? So essentially, on an average, that's the total charge that you are generating into the semiconductor bar per unit time. Okay. Okay, so I want you to think about this problem a little bit because it's not as straightforward, and we don't have a lot of time to go through it. So make sure you go back and look through it, okay? And you understand it. Okay, that brings us to the next chapter, actually. So let me open up the next one. Actually, it's the last part of the chapter 4, let's say. And hopefully we'll start chapter 5. Yes. Area. This is the cross-sectional area. Yes. Well, it's a uniform bar, so anyway, that's the idea. Okay, so the first topic that I wanted to cover today is the last part of the chapter 4, which is an equivalent experiment that we saw before. Remember we talked about the Hall measurements before? Recall the Hall measurements. The Hall experiment was a very elegant way to measure the majority carrier properties like mobility and something else. Oh, I forgot. There are 2 parameters. But anyway, you can go back and look. Mobility and something else. Yeah, anyway, the concentrations, of course. The Haynes-Shockley experiment is the analog for the minority carriers. So it's a bit more complicated. It's not as simple as the Hall effect. Okay? The Haynes-Shockley experiment is also very important historically, and I've posted some extra material online so that you can take a look. So essentially, it allows you to calculate the minority carrier mobility and the diffusion coefficient. Recall that we need to know the minority carriers can have a significant impact on current because they diffuse under concentration gradients, and the the gradients can be quite large. So that's why we need to know this. Okay. So the experiment is very straightforward, but to do the measurements is a little bit tricky. So it's again the same example that we saw here. Okay, we have a long semiconductor bar, and a current is flowing. Okay, you apply voltage, a current is flowing. Okay, just like before, that's the drift current. Okay, you generate locally a pulse of electron-hole pairs, and this could be done a number of ways, and we'll talk about two ways here. One is with light. So imagine a laser pulse which is hitting the semiconductor bar in a very small focused area. Okay? Of course, the photons from the laser will excite electron-hole pairs, will create large quantities of electron-hole pairs locally. So you will generate a very sharp pulse, as shown here. So this is N-type bar. We're only plotting the hole concentration. We're interested in the minority carriers in this case. Okay. So we have a pulse at t equals 0. You have a pulse of holes, and of course, if you turn off the light, now the pulse will diffuse. But remember, there is already a drift current, so it will drift also. So you have drift and diffusion at the same time. So you can count for both. Of course, it will diffuse, meaning it will move in the field and move according to the concentration gradient, which is what we saw before, that it will spread, basically. That's diffusion. But it'll also move, as shown here. So you have a spread here, but it's shifted over. You'll have another spread here, shifted over, another spread here. It'll move because of drift. Okay? The holes will move along the electric field. So you see the picture of what's happening? Okay? Of course, there's recombination also. So we have many things going on here. Okay? So the question is, the mobility of the minority carriers determines how long does this pulse of holes here reach, say, some distance here. It's of course spread out, but it takes some time for the holes from here to reach here. That, of course, is determined by the mobility. It's a response to the existing field. Okay? The diffusion coefficient, on the other hand, will determine how much they spread out. So starting with a very sharp pulse, you spread out. How much has it spread out? So this experiment is a very elegant way to measure these two quantities. Okay? For minority carriers, remember, keep that in mind. Remember, for majority carriers, the diffusion can be ignored, right? Because the excess carrier concentration is very, very, very small, basically. Because remember, you have 10 raised to 17 electrons, and if you generate another 10 raised to 10 electrons, that's nothing, right? You have 7 orders of magnitude higher. So basically ignore it. Okay, so we make the assumption it's N types, and naught is much larger than P naught. So excess holes generated is significant, but excess electrons is small compared to N naught, as I just said. The drift velocity, which of course determines how fast the holes move in the electric field, is given by L over TD. Okay, I can hardly see, it's a little small. Oops. Yes, you can see it. So VD, the drift velocity, is just the distance L divided by TD. So the distance L is the distance that the holes have traveled from here, x equals 0, to here, x equals L. And TD is the distance, is the time taken by the holes to travel from 0 to L. Okay, so that's the average drift velocity. Okay? And the mobility, of course, is the drift velocity divided by the field. This is definition of mobility. Then recall that the Hall effect measures majority carrier mobility. Here we measure the minority carrier mobility. So what you do is, again, you do the same, the system is the same, but now you need to monitor. So you need to generate this pulse at some instant of time. You need to monitor some distance down to see when the pulse arrives. Okay, so you see with the oscilloscope, you look for a current. Okay, it's a steady current all the time. You generate a pulse. Okay, and then you wait. You will see another pulse arriving in the oscilloscope. The time difference between them allows you to measure the drift velocity and hence the mobility. Okay, so that's basically the principle of the experiment. The experimental setup is a little more complicated, as we will see in a second. Okay, now we can simplify the diffusion equation. Let's just look very quickly at the equations if we ignore the drift and the recombination, so remember those x's terms, then we can write the diffusion equation as follows. This is basically assuming that there is no field, so the whole thing is not shifting, it's just spreading, okay, just the diffusion. And we're ignoring recombination for the time being. We'll introduce it later. The solution of this diffusion equation turns out to be a Gaussian, and I won't derive it. It's essentially a Gaussian distribution where the peak of the Gaussian, so this is a function of space and time, first of all. This is excess whole carrier concentration. It's a function of space and time. There is some peak value here multiplied by some exponential, some Gaussian term here. Okay. Now, if you look at the peak value, it's inversely proportional to time. So as time goes by, the peak goes down, which of course is what you expect because it's spreading, right? This is the spread of the Gaussian. As time goes by, the whole thing is spreading further out because this is inversely proportional to t as well. Okay? So that basically defines just the spreading component, not the drift, but just the diffusion component. Okay? So, of course, the equation looks like this. So if we take the plot looks like this. If we take a snapshot of the whole concentration at some instant of time, okay, it will look something like this. So it's a Gaussian distribution, okay, with some peak value. Here we have ignored drift. If we had drift, we know this whole thing would have shifted, right? 1bx equals 0. So let's ignore the drift for the time being. We just have a simple Gaussian distribution where the peak is now given by that first term, and this spread of this Gaussian, this delta x, is given by that, basically where the peak falls to 1 over e of the peak value. Okay, so it's just a Gaussian distribution. As time goes by, this peak goes down, and this delta x increases, as you expect. Eventually, it will just become uniform. Okay? So let the concentration fall to 1 over e of the peak here, and you can derive what the spread is, essentially. So this, if you set 1 over e of the peak value, then this exponential term becomes minus 1, equals 1. Okay, then you get the diffusion coefficient can be expressed as delta x squared divided by 16 times td. So this allows you now to measure the diffusion coefficient by looking at the spread of that pulse after a certain time td. Okay, so if you, in your oscilloscope, if you can measure the pulse spread, okay, because you're seeing it over time, right? Oscilloscope is monitoring, as we will see, monitoring a single point in space, but in time. So you'll see a pulse travel by. Okay, so you can plot it in time, right? You'll see a pulse travel by in time. And you can measure this width in time and relate that width in time to a spread in space, as we will see in a second. Okay, so if we know that spread in space and the time that we measured it at, then we can calculate the diffusion coefficient. Less idea. Okay, let's look at the experiment. Okay, this is what it looks like. So we have an n-type bar, as we saw before. You have voltage being applied and a current flowing. Okay, straightforward so far. Okay, I, E naught. Okay, now we have a pulse generation here. Now the pulse generation, like I said before, could be a pulse of light. In practice, it's not done with a pulse of light, it's done with actually a transistor. And we'll learn that later on, but it's essentially a whole, forward bias PN junction can be treated as a whole injection, right here. So you have some x equals 0, where you inject extra holes. Okay? Then you have a location here, where you do detection of this pulse of holes. And it's typically done with the reverse bias PN junction. We'll see this later on, but imagine there's a way to measure it. Okay? And then you send it to an oscilloscope, the signal from there. So you're just looking at a pulse in time. Okay? Then what you see on the oscilloscope looks kind of like that. So what you measure in a scope is typically voltage, right? For those of you who have used before, ignore all that, but basically what you see is the voltage. And what you see in voltage is essentially the voltage is a function of time. So you have a single point you're monitoring voltage, and for a long time there's a fixed voltage because there's a fixed current, right? There's a fixed potential. Then after a while, it starts going up, and that's the pulse arriving. Okay, so you have a starting point when you have a little pulse. That's when you generated the pulse. Okay, that's t equals 0. Then after a certain time td, the actual pulse arrives. This is the pulse of holes that have arrived at this location, and of course it's spread out. So you have two things that you have measured. You have measured td, which is the location of the peak of the pulse in time, and the spread of the pulse in time, delta t. Of course, with td and knowledge of this distance L, this distance between point 1 and point 2, you know the drift velocity, right? That distance divided by time is drift velocity, because that's the drift of the holes. Once you know the drift velocity and you know the electric field that's applied, yes?
What value of the voltage is the spread in time?
What? No.
Like it could be. What's that?
Yes, that's correct. Yeah, a good point. Yeah, because that's what we talked about before. It's a Gaussian. We assume it's a Gaussian. Now we'll relate to that in a second. So by knowing TD and the distance that the holes have traveled, you know the drift velocity. Knowing the electric field, because you know the potential that's applied and the length, you know the electric field. You know the drift velocity in the electric field, you know mobility. So now you know the mobility of the minority carriers. Okay? To calculate the diffusion length, you need to know the spread of the pulse. So we need to look at this delta t and relate that delta t to the spatial spread of the pulse. Of course, to do that is very straightforward. All you need is the drift velocity. Okay? So we can, of course, measure this pulse width in time. You cannot measure it in space because you only have one point that you're monitoring with the oscilloscope. Okay? You're not measuring in space because it's very small. You can't really measure in space. Then you can relate that spread in space to the spread in time by multiplying it by the drift velocity. Right? Because the point of the pulse, if we are assuming a constant velocity, if you have a pulse which is traveled a certain distance, that part of the pulse travels an extra distance, that gives you the spread, right, basically. Anyway, that's just common sense. So delta x is delta t times Vd. And then by knowing delta t and Vd, you can calculate delta x. Okay? So, of course, once you know delta x, you know the diffusion coefficient, just like we just looked at before, right? The diffusion coefficient is just given by delta x squared divided by 16 times dd. So what this experiment has allowed you to do, again, so it has allowed you to measure experimentally the mobility of the holes, the minority carriers in an n-type material, and the diffusion coefficient of the holes. These are two fundamental material parameters, and they're very difficult to measure typically. This gives you an elegant method of measuring them, especially for minority carriers, very difficult to measure. Remember, because minority carriers, there's only very few of them compared to the majority carriers. It's always very difficult to extract their properties. So I want you to understand this. It's not trivial, but it's not that difficult. So think about it. Okay, so let's look at this particular example problem. And again, I want you to think through this yourself first before we look at it. Okay, so in n-type, it's the same example we just looked at. You have an n-type germanium sample. It's used in the Haynes-Shockley experiment shown in the figure. The length of the sample is 1 centimeter. And the probes 1 and 2 are separated by 0.95 centimeters. The battery voltage is 2 volts. The pulse arrives at 0.25 milliseconds after injection at 0.1. The width of the pulse delta t is 117 microseconds. Calculate the hole mobility and the diffusion coefficient and check the results against the Einstein relation. So let's first calculate the hole mobility. That's the easy one. Okay, talk to your neighbors for about 15-20 seconds. This should be easy. So, okay. Okay, so to calculate the whole mobility, what do we need? Oh, come on, someone should check this out. So we need to know mu p. What is mu p? Yes, so it's the drift velocity. It's a function of the electric field. Right? This is the definition of mobility. Now, what do we know? Do we know the electric field? Yeah, what is the electric field? So that's the voltage applied divided the total length. So it's 2 divided by what, 1 centimeter? Is that right? The 1? Yeah, because that's the total length, right? Now, so we know this. Now, what is this? The drift velocity is just the time it took the pulse to reach that distance, right? So that's the distance traveled, which is what, 0.95 centimeters? That's when the distance between the pulse generation and the pulse detection, divided by the time it took to detect it, which is what? What is it? 0.25, right? Isn't it? Milliseconds, yeah. So it's 0.25 milliseconds. Okay, so now you know mobility. Is that okay? Be careful with the units, obviously, right? That's another thing that people make mistakes. I don't particularly care because as long as you know how to do it. Right? Okay, so that's the easy part. Now, what's the diffusion coefficient? Okay, the diffusion coefficient. We assume that the Gaussian, and obviously you will have to look it up, but you should have good memory. That you should remember that this is assuming a Gaussian is related to the spread of the pulse or something like that. Right? Delta x squared divided by 16 times 3p. Now, what is delta x? That is the spatial spread of the pulse, is the time spread of the pulse multiplied by the drift velocity. Right? So what's the time spread of the pulse? The width of the pulse, delta t, is 117 microseconds. So 117 microseconds multiplied by the drift velocity, which we know from here. Right? Okay. So this is just, oh, no, sorry. This is 6.25. Okay? Pretty simple. Okay, TD is just the time, right? The pulse region. Plug everything in, you get the answers. Now, what was the Einstein relation? Does anyone remember? Einstein relation, of course, relates the drift to diffusion. It's a very fundamental relation. And essentially, it's basically what? It's like dP divided by mu p is a constant, basically, right? Or dN by mu n is a constant. What was it? I think it was KT over Q or something. Yeah. We call that's an Einstein equation. All the problems is asking you to do is just to, you've calculated these two things, with dP and mu p, just divide them and make sure it's equal to KT over Q. It should be. Okay, that tells you a different issue. By the way, KT over Q is always about 26 millivolts at room temperature, 300 Kelvin. Okay? So just, you don't need to actually do Boltzmann, you don't need to multiply that, if you just remember that. So it's a very important constant. Now, this tells you that we don't actually need to measure both of them independently, as long as you know the temperature of the bar. Right? You only need to know one. When you apply Einstein equation, you can calculate the other. Okay? So keep that in mind also. So you can simplify your life considerably. It might be easier to just do that rather than doing all this right? Okay. I'll give you a minute. But the last part of the class, I wanted to introduce the PN junctions, and we're going to talk about modeling PN junctions and understand how they operate, probably the next couple of classes, okay? PN junctions, as we saw before, what they are, but basically they are the most fundamental devices in semiconductor physics. A PN junction is a diode. And if you recall, a diode was an op-amp. I don't know if you did your freshman electrical engineering, maybe. That's when I learned it. Op-amps. Is that correct here? Okay. So op-amps are basically diodes, right? You allow current to flow one way, not allow current to flow the other way. And that's a PN junction, basically. Okay? The physical device is a PN junction. You probably drew it as just a little op-amp and made circuits out of it. Okay, so now we're going to understand how it works. And this is the basis for transistors and everything else, so we need to really understand this. Okay, so we saw PN junctions before. Essentially, it's a N-type material in intimate contact with a P-type material. There are many different ways of manufacturing these, and they're fairly well described in the first part of Chapter 5. So I'm not going to go through it in the interest of time, but I would encourage you to read it if you're interested. But there are lots of ways you can generate these. Essentially, you take a piece of silicon. On one side, locally, you dope it with, say, boron to make P-type. Right next to it, you dope it with, say, phosphorus or some, group 5 material to make it N-type. That's it. They're locally done. And you do this with lithography. Essentially, you can pattern these areas and so on. And doping is typically done by what's called ion implantation, or you can do it chemical doping. And we talked about a few of these early on, but there are lots of different ways we can do it. So if you're interested, make sure you read that. But if it's important for understanding, I'll point it out. So for us, we'll just think about this as a cartoon picture as this. Okay? So the first, we will make the assumption that it's a sharp PN junction. In other words, it's an infinitesimal change. So you have a P-type material shown in red, okay, and it's a very sharp boundary here, and then you have an N-type material. In practice, of course, nothing is infinitesimally sharp. You can never get a sharp infinitesimal change like that. In practice, it's different. But for most modeling purposes and for most devices, this is a good approximation. And when it's not, we will emphasize it, okay? So that's the first approximation. So essentially, you have P-type, you have lots of holes here. N-type, you have lots of electrons here. And we assume it's uniform doping. So you have uniformly doped regions, except right at the boundary where you have the sharp change, right? So obviously, that's not uniform. But away from the boundary, it's all uniform doping. Okay? So the basic assumptions are your infinitesimally sharp boundary. And for instance, this can be achieved with epitaxial growth, which we talked about before with respect to quantum wells and so on. So a couple of things. At equilibrium, there is zero net current. But remember that a built-in potential exists to prevent the diffusion current. Okay, well, we'll review that, but we saw that last class. Okay? So keep those pictures in mind. Okay, so the built-in potential is referred to as a contact potential. Now we will try to quantify this, try to calculate what that is. So again, we have a situation. You have P-type semiconductor, N-type semiconductor brought into intimate contact. What happens? Okay, you essentially, if you look at the band diagram, it's fairly straightforward to understand. You have the P-type semiconductor with the Fermi level closer to the valence band. That's the N-type, sorry. Valence band. No, that's the P-type. The Fermi level closer to the valence band. And then you have the N-type with the Fermi level closer to the conduction band. Of course, when they're in contact, remember we talked about the Fermi level cannot change in space. You cannot have gradients unless an external potential is applied, as we saw in the... We will see again, but it has to be constant. So when you put them together, the Fermi level has to be flat, which means that the two bands have to bend on two sides. Okay? So you have a bending of the conduction band going down, your bending of the valence band going down, and this bending difference between the conduction band on the P side and the conduction band on the N side is the contact potential. That is the picture. Now we'll calculate this. but that's the picture I want you to keep in mind, okay? The electrostatic potential, of course, you can draw as follows. You have a potential on the p-type, and you have potential on the n-type, and they're different. Potential, of course, they're different because the Fermi levels are different. Okay? The potential on the n-type is higher than the potential on the p-type. Okay? This built-in potential barrier prevents further diffusion of carrier. So let's recall what that means. So this side, so let's look at this situation here. This side has lots and lots of holes, right? This has very few holes. So obviously diffusion will force the holes to move from left to right, right? But you cannot have current in equilibrium, which means that something must prevent it from moving from left to right. Otherwise you will have current. And that something is the field. Okay, and which way is the field pointing? Which way would the holes flow if there was no field? I just said that. From p-type to n-type, right? From left to right. So the field has to prevent it, needs to point from right to left. Right? Remember, holes always move in the direction of the field. So the built-in field is pointing from right to left in this case. Okay? Same thing for the holes. Holes, of course, there are a lot more holes here. Actually, before we do that, remember the holes try to go up the hill. Remember, they try to minimize the energy. Energy of holes increases down, so they try to go up the hill. So that's another way to think about it. This is the energy barrier for holes. There are lots of holes here. It sees a downhill. That's an energy barrier. It prevents the holes from going through. It's another way to think about it. Okay? This sort of logic will become very natural to you because all the analysis of devices have to be done this way. Now let's think about electrons. Okay? There are lots of electrons on this side. Very few electrons on this side. Of course, electrons will move from right to left. Right? This way. So the built-in field has to prevent that motion, which means that the field also has to point in the same direction. Because remember, the electrons move in the opposite direction to the field, so the field again points from right to left. From an energy perspective, if you think about it, electrons move downhill. Right? Electron energy goes up, so electrons like to minimize the energy, they move downhill. Right? We saw this before. So if the electron is sitting here, it sees an uphill here, which means that's an energy barrier. The electron cannot naturally go that way. So it's preventing that motion. That's the built-in potential. It's preventing that motion. So the built-in potential barrier prevents further diffusion of carriers. Some diffusion, of course, occurs, and that's what generates the built-in potential. Okay? And the picture is as follows. Okay? Can't see this. Oh, we have time. Okay, good. So the picture is as follows. So you have a p-type, n-type. What happens is that the holes here will. Okay, actually, we should probably throw this. So this is very basic, and you need to understand this. So imagine p-type, n-type. Let's just concentrate on the holes. The holes, of course, will move. Okay, move this way. What does that mean physically? The holes moving this way means the electrons are moving this way. So just accept it on this side. So which leaves positive charges on this side. Okay. So you end up generating positive charges on this side. So the holes have moved over. The electrons, of course, move from this way to this way. This is just the diffusion. High concentration, low concentration, and you generate negative charges. Now, physically, what this means is that the electrons get captured by the silicon atoms, for instance, and you have uncompensated acceptors here. So essentially, charge neutrality is broken. You have excess charges here. Okay? We'll look at that more carefully. But essentially, you generate some charged regions here. Of course, outside this region, it's neutral. Outside this region is neutral. But within this boundary, you generate charges in this way. Of course, with this positive charge, negative charge, the electric field is this way, right? Which is what we just drew. Okay, everything is consistent. But that's the picture. Okay, that's the picture we drew here. So you have a distance W, which we can refer to as a transition region between the p-type and the n-type, where the charges exist. okay? And the electric field is pointing that way. Outside, there are no charges. That's a neutral region, okay? Excess holes here diffuse this way. That leaves uncompensated acceptor ions, creating a negative space charges, okay? Remember what that means. In the p-type, there are acceptors which have accepted the electron. And there are holes floating around, right? If the hole is around and an acceptor is there, remember the acceptor has taken an electron, it has become a negative ion, right? It's accepted an electron. Okay? And the negative ion, charge of the negative ion is compensated by the hole that's flying around. But if that hole's gone, now you only have a negative ion. And that's what's here now. Uncompensated acceptors. Okay? The same thing happens with electrons. Electrons move from P to N, N to P. This leaves uncompensated donors, creating a region of positive space charge. Remember, the donors are basically you lose an electron, and then it becomes a positive ion. Right? And again, the charge of the positive ion is balanced by the charge of the electron. If the electron is floating around, but if the electron's gone, then you have a positive ion sitting there. So you have a positive charge, as shown here. Okay? So you get a built-in field which prevents the diffusion current, prevents this motion of carriers. Okay? So at equilibrium, there is no current flow. We saw this before. So if you look at the particle flow, you have the whole diffusion going from p-type to n-type. You have the whole drift going the opposite way, because the field is pointing in that direction. And then you have electron diffusion going from n-type to p-type, and the whole electron drift going the opposite way. And each of these must cancel each other at the current, right? So if you look at the current, the whole diffusion current is the same direction as the flow. Whole drift current is the same direction as the flow. The electron diffusion is the opposite current as the flow. Electron drift is the opposite direction as the flow. These two should cancel, and these two should cancel at equilibrium. Okay? And in the next class, we will write down equations for these and cancel them out, and then we can derive the contact potential. Okay. Okay. So the problem set's due today, and I don't have the problem set 3 yet. Most likely, I'll have it on Tuesday. Okay.